Bigger notation. What is time complexity and space complexity? Now, let's think about algorithms as a trip that we want to take. And then the data structures are actually the vehicles that we might use. It could be a bike, it could be a car, or it could be a plane. As you can imagine, one is faster than the other. And also, different trips might have different vehicles involved and therefore different speeds. Now, with time complexity, if we're taking a bike, let's say a really expensive long trip, then you are going to have a really long algorithm. Like it will take forever. You want the time to be as short as possible. Now, we are not going to measure in time complexity the time in seconds or minutes or hours. It's just a time abbreviation. You want either constant, linear, logarithmic. We're going to get into those details, but the faster the algorithm runs, the better. Now, how do we actually know what is faster or slower? Well, it depends on the actual input data that you are going to give this algorithm to. So let's take a look at the graph that I have prepared right over here. As you can see on the x-axis, we are increasing the size of the input data. And here on the y-axis, we are representing the time required to go through all of that. Now, the green one, which is the preferred one, is constant time. So the time that this algorithm will run, it doesn't really matter if it the data has 10 elements or 100 elements or a million elements. For example, if you are having a list and you want to access its first element, it doesn't really matter if the list has one element, 10, 100, or a million elements. You are going to access that first element instantly, in constant time. That is O of 1. For example, the first element of the array. Think of this like the speed of light. Now, we have O of log n next, but we are going to jump into the explanation of O of n because it's a little bit simpler and you are going to understand O of log n much easier if you understand O of n. Now, O of n means just consider, let's say, a list of names, and you want to find a particular name. Now, if that name is the first name, then of course we are in O of n, but if that is not the case, and most probably it isn't, then you are going to assume that it might be at the very end of the list. Therefore, you want to go through all of the elements on that list. And because you have 10 elements, then you just need, let's say, 10 seconds. If you have 100 elements, you are going to need 100 seconds, and so on. Therefore, the time complexity will increase linearly. As the input size increases, the time required also increases. So that is O of n. Now, let's debunk this O of log n. What is it actually? Well, think of it like you have a word and you want to search the dictionary for that word. Now, how would we do that in O of log n time? Well, we're going to open up our dictionary right in center. We're going to check, is our word that we want to search for in the first part or in the second part of our chunk? If it's in the first part, let's just say that it is, we are going to throw away that second part of the dictionary. You know, we don't have to go for the way through like with O of n. Then we are going to chunk that remaining part again in half. And again, do the question, is it in the first part or the second part? Let's say this time it's in the second part. Okay, do the chunking in half again. First part, second part. And then we are going to throw away half and half and half and half and half of the remaining data until we get to our result. This way, we are not going to traverse all of the dictionary like we would have with O of n. We are going to traverse it in O of log n time. So that is much more optimal. Now, I have also added two more, O of n squared and O of log n. Let's tackle the most expensive in time complexity, meaning O of n squared. Now, what would that mean? Think of, let's say, a class of students, and you want each student to shake hands with every other student. So if we have 10 students, that would be 100 handshakes. If we have 100 students, that would be 10,000 handshakes. As you can see, it will take a lot of time doing that. So consider this, if you are, we are going to take it in the coding perspective, it would be a for loop within a for loop. So we are taking an array of students, and for each and every element of that array, we are going to go through, loop through again, every element of the same array. As you can imagine, that will take a lot of time. This is not efficient. And this algorithm would run in a really, really long time. So you want to come up with something else, a new algorithm for that particular problem. I also added in here O of n log n. And basically that's log n, but multiplied by n. I added this over here just so you know where to put it. O of n log n is the time complexity of most of sorting algorithms. You are going to bump into this in the following sessions. So that is where you want to put it. It's less than O of n squared, but more than O of n. So that's where you are going to put it. Now, if your algorithm uses one or more of these time complexities, you are always going to use the one that is most expensive. And basically that's it. Now, let's talk about space complexity, which is basically the same thing, but not in time, but in space. How much space will it take? If it's constant space, right over here, then it's basically not using any extra space. If it's O of n, it's just going to reuse the same space again, and so forth. We are going to add for each and every algorithm that I'm going to solve in this series, the time complexity and the space complexity. So, and I'm going to discuss on that algorithm why that will be the case. Now, these are just a few and most important ones, but there are much more than this. And if you want a deeper dive into this, you don't really need to memorize all of this. Maybe you just need to be aware that are more of what I have already covered, but those are just the basics. This site, bigocheatsheet.com, and yeah, you can just take a look at all of the time complexities and space complexities. One word over here, there's average and worst. You should always expect the worst, but in some algorithms, you can also manage an average. Space complexity is always the worst, calculated on worst. There's no average on space complexity. And also, here's a quick cheat sheet on array sorting algorithms if you fancy to take a look at these.